I can hear
Okay.
you. Could you hear me?
Yeah, that's good.
Yeah,
And
can you see the screen?
I can see the screen. And
Okay, I enlarge it. And what about now?
it's perfect.
Okay, so let's start. Thank
Yep.
you very much for the invitation. I'm very happy to be back. I would like to say some words first about Georgi. We met first time in at a strange conference that was Condensed Matter Division of European Physical Society. At that time I was about to finish my PhD, and my PhD was concerned with quantum theory of electron transport in liquid metals. So it was quite strange, but my boss, Professor Jan Popielawski, wanted to change the main research area from amorphous system into stochastic chemistry, non-equilibrium chemistry. And it comes out that Professor Popielawski was at postdoctoral stay at University of Chicago at the same time Georgi Nikolis was there. So they met together and they knew each other, and maybe the activity of Georgi influenced my boss to decide about the subject. And he suggested me to go to the lecture at this conference, to the lecture of Georgi, and listen to it. And then I had some opportunities to visit Brussels for conferences and for short research stay, about 10 days, as I remember. 1981, and well, I'm still in the field of far from equilibrium chemistry. So let me go to my subject. So my subject is information processing, and what is the motivation for chemical computing? You know, well, everybody uses brain every day, so chemical computing can be bloody efficient. Why not try to do the same in a test tube? And well, we have a very strong competition from semiconductor industry, because within many years, semiconductor industry was able to produce fast and reliable logic gates that operate for long. So I think the technology implies bottom-up design strategy for semiconductor-based computing devices. We have reliable logic gates, we can build more complex structure, and well, the theory of information or computing devices matches perfectly the technology available. Actually, you can make logic gates with computing, and here I show you an experiment done by Yasuhiro Igarashi. Here you're supposed to see were you able to see two pulses of excitation propagating on the dark background. This is a photosensitive busy reaction. They collide in the center and disappear. So you can imagine there are two inputs. We load those inputs with signals. The signals, oh, doesn't work. No longer, that's typical. The lifetime of chemical information processing devices is very short. In this case, it's a membrane loaded with reagents of busy reaction, and well, you can produce a couple of pulses. They come together, they annihilate, but if you have a single pulse, can you see my cursor? Sorry, can you see the cursor?
We can see it, yes.
Yes, okay. So here is a pulse initiated, and you can see it propagates. Here is a single pulse. There is no pulse in this channel. Okay, it propagates to the center area, and it comes to the output. So actually, we can say, okay, this is an XOR gate made with photosensitive reaction. Well, you can claim, oh, well, we can do everything real computing can do with chemistry, but this is very slow. So a better approach is to use a computing medium as it is and use top-down design. So we have a computing medium. We have to decide what computing medium we are using, how to describe its evolution, what are the control factors, how to input the information to the medium, and how to read out the medium answer. And then we can try to optimize this medium for a selected task. For example, in a recent communication by Lee Cronin group, they selected a reactor. It's a kind of tank reactor. The liquid inside is busy medium. Those objects in the centers are stirrers, and busy reaction is controlled by stirring rate. And so in each cell you have a stirrer. Stirrer controls the progress of busy reaction, and there is an influence interaction between cells through the holes, and the holes should have a special geometry. I think this is, roughly speaking, 1 centimeter size object, and they can do, actually they publish a paper on logic gates. This is not a special progress if you compare with the other medium, but this is an interesting medium to try. Well, how to read the medium answer is very important, and let me go a bit off topic, maybe not totally off topic. I was working in Japan for a long time, and actually one was my collaborators and friends was Professor Kazuo Kitahara. And Kazuo was the last graduate student of Ryogo Kubo, but he actually did his PhD thesis in Brussels in late 70s under the supervision of Professor Nicolis. So actually, thanks to our contact with Brussels, we had a lot of ideas to share. But let's come out to this big fish. It's called Onamazu, and it controls earthquake in Japan. So we can use a smaller cousin, another catfish, as a computing medium. And actually such experiment was running for 16 years in Japan. And the idea was, okay, maybe this cousin can contact Onamazu and get information about an earthquake. It came out that maybe the fish can get information, but actually we have no reliable method how to read out this information. So reading the information from a natural computing medium is not that easy. Okay, I'm not that ambitious as showing you an earthquake prediction problem. I consider myself database classification problems. So assume we have a data set that is composed of predictors, inputs, and a type of the data set. For example, logic gate can say, we can say, okay, the predictors are the logic inputs and the type is the output. We can have geometrically oriented problem, and then I'm selecting a random point, and the database contains information. Is the point, does the point belong to white or to the red area of the picture? So, well, there are of course problems inspired by real life, and for example, medical tests can be used as predictors, and the diagnosis is the record types. And what I really want is to make a medium in which we can input predictors and we can read out which type of record it describes. So I will consider this problem as an example. Now let me come to chemical computing with an oscillator network. I consider a network of oscillators in which we have oscillators are interacting, and we have two types of oscillators. Oh, I've forgotten to tell that each oscillator can be individually controlled by an external factor, and this is very important. This external factor can be illumination. There are two types of oscillations. For some oscillation, this illumination, the external control factor, is fixed. So let's say I start at time is equal to 0, and this particular oscillator starts to be active at time 10 seconds. But there are input oscillators, and for the input oscillators, the time of inhibition is related by an affine function with the value of predictor. So this is the way we input information to the network. And there is a problem how to read out the information. And in the simplest case, the number of, I assume a certain simulation time or center of observation time, and the number of oscillations seen within this time is my output. Of course, I don't comment on it because of lack of time. You can use more complex method of reading the information. It's important that the observation time is finite. So actually, I do not study what is the steady state of the system. Let me show you this movie. That's a prototype of potential computing medium. There are droplets with busy reagents, and you can see they are blinking. But within time, the character of the interactions and the character of evolution changes. Now this one controls the whole medium, and then this control switches to this droplet, and finally it dominates the evolution. So I do not study the long time evolution. I study the number of droplets I can observe within a short time. So now let me come to the problem. Oh, sorry. So how to design a classifier? It's funny, I can tell you, okay, this system does a following type. So first is have to have a good idea, but usually we don't have. So another is to use optimization algorithm. To define the structure, I should tell what is the geometry, what is the model that usually are predefined, but where are normal oscillators that are inhibited for a given time, irrespectively of the predictor value, where are the inputs and how to read the information. I should provide all this information, and it's a lot of it. So our favorite is genetic optimization. In genetic optimization, we generate a number of networks in random. Then in random, we perform recombination between parents, generate an offspring, and this offspring undergoes mutation. And for the next generation, we select the best offsprings and repeat this procedure to go on and on. So this works in an algorithm. Is pretty straightforward, but lengthy. So let me come to an example problem. We consider a network of just 3 oscillators. Each oscillator is described by organator model. For interaction, we use reactions that couple activators of oscillators. We have additional control of activator concentration by adding another reaction. And finally, we have the evolution of the network. So actually, we fix the networks, we fix the parameters of a regulator model. What we don't know, what is this oscillator and how it should be illuminated, and what are the constants alpha and beta that describe the evolution. And of course, we don't know how long we should observe the system. But remember, just 3 oscillators. And here is our problem. 800 elements distributed, 800 points, randomly distributed in a unit square. And we optimize it to match the best mutual information between the number of oscillations on one of those oscillators and the type. The type you can see here are red points, here are blue points. And this is the result. The number of cases, the number of oscillations. Single oscillation is more likely that the point is inside. 2 oscillations, the point is probably outside. Okay, there are some mistakes. Here, this is the evolution on the output droplet. It came out to be number 3, which is pretty nice because the system is symmetric. And if we select a point somewhere here, we have just 1 maximum of activate. If we have a point somewhere here, then we have 2 maximum. Okay, pretty nice, but I'm astonished. 95% 3 oscillators, not a lot of computation to be done. But you may not trust me. So this is a test of this classifier. Using this type of result, we can select the classification rule for the small data, training data set, and apply it to a large data set. And this is what we come out. The red points are classified are those being inside the red area. The blue points are outside. Well, you can see, okay, it's not a disk, it's a kind of horn disk, but then we can reverse the question, saying, okay, but actually what we've done is not the best classifier for the disk, but a classifier for the structure. This is bounded, which is bounded by two curves, quite sophisticated, you can estimate them, and for such object, classification is 99% of accuracy. And those curves are not trivial. So actually non-trivial problem can be solved with just 3 oscillators. So remarks to after my talk, even a few chemical Kaput oscillators. Consider performs of computation in the optimum way, and the information is hardly parallel, so no oscillator is all these oscillators are necessary. The network the network accuracy strongly depends on the model, so it's meaningful to say for the model. Well, such computation is not supposed to be perfect, but we hope to obtain a network that operates for acceptable accuracy, and optimized networks are not building blocks. They are designed just for specific. So thank you very much for your attention, and I leave you this slide where I thank to my collaborators, and you can, if you are interested, you can find references to our works. Thank you again, and if there is time, I'm ready to accept questions.
Thanks a lot. Well, I think we have time for a short question, and so maybe I think Valerie was first to raise her hand. So maybe you can go forward.
Hello, thank you very much for your nice talk. Regarding the size of your droplets and...
Sorry, could you speak louder? Because
Yes, I'm trying. So regarding the size of your droplets and the fact that the BZ reaction is involving a lot of different components, do you observe any kind of noise effects?
Well, okay, what I said is in silico study.
Okay.
Yes, noise effect is not extremely important if you go to real experiments. We're experimenting with BZ droplets. It means droplets with BZ reagents surrounded by phosphorolipids. And that was the movie I was showing with those complex oscillations. And the main problem with this system were the bubbles of gases, probably CO2, that appear at the edge of the bubbles. And actually such system, it's very difficult to stabilize such system for a very long time. So now we moved into reactions in Dovex beads containing catalyst and surrounded by the other reagents, by the liquid medium with the other reagents. And I've got a postdoc, Franciszek Muzyka, and he is able to produce stable oscillations on Dovex beads for, well, half a day or even longer. So I hope to reproduce some of the results with experiments pretty soon. But of course, there is no restrictions on the model of oscillations. So actually you can use more stable oscillations, even well, electronic one, to reproduce this type of information process.
Thank you very much.
I see that Jerzy is really wants to ask a question. So please go ahead.
Okay, yes, Jerzy, what I wanted to ask is, how sensitive is the system to, let's say, the shift of conditions? You know, instead of an open system, let's say we have batch. So slowly the oscillators shift their, I mean, the limit cycles change itself. How?
Yes, but well, what Franciszek was showing me recently he can stabilize oscillations on Dovec's beats for, let's say, 6 hours with the period around 10 seconds. So yeah, and this is of course batch system, so we do not know load. The consumption of reagents is so small that I believe it will be stable.
Okay, thank you.
Well, thanks again. I think you have a lot of questions, but remember that you can also go to the Meet Anyway link and discuss with people afterwards. I'm sure there will be many questions again, but thanks again.
Thank you very much once again.
And
yes, yeah. I'm supposed to stop sharing.
Thank you.
Yes.
So we can move to